address for global, the global gpio address requirement, and the alias will be gpio address to register 0. Now we're gonna load the gpio address at this address, which is 0202000, which stores the gpio controller in the address register 0. And now we're gonna move the return address, which copies the registry to program counter, into the program counter, and we're gonna delete the alias for the gpio address. Now we're gonna do the global gpio function, which is the number request for the pin number request, which is 0 register 1 alias, and pin function which is in register 1 0, and then register 1 request. So this lab, the code is very similar to lesson 3, I believe so, and also similar with lesson 4. So basically we compare the pin number 53, compare the register 0 with 53, as we know that the GPIO has 54 pins from 0 to 53. Then the pin function number 7 is compared to with the comparison of register 0 and with number 53 as a GPIO pin. Is if it's lower than or equal to 53, then it compares registry 1 with 7. So we know that it's gonna go, we know it's registry 1 performs 8 functions for each pin, 8 function pins, which can perform from 0 to 7. We move high with the return address does, so basically it's going to do return address again, which does not run, and then if we met higher than 53 or 7 with a program counter, basically we push the return address, which copies the value in return address to the top of the stack currently at register 0 if above conditions are met, like so. Basically we move the registry 2 pin number and move the GPIO address from registry 0 to registry 2 to ensure like if it's like not overwritten. And then the pin number, we deleted the alias, and then the pin number, we create the alias, which is a call function for the get GPIO address. The GPIO address is a registry 0, which creates the alias for the address itself. Then it uses a function loop, compares the pin number 9, which current pin number to 9, and then it subtracts the pin number, which is 10. If higher than 9, subtract 10 from the pin number, and then it basically adds the number 4, adds 4 to the GPIO controller, and does a function loop, which runs again pretty much. The rest of the code is pretty like similar from, I believe, it's pretty similar code from lesson, I believe, 4, where it uses the binary code and deletes, and it does the, so basically the remainder of the old function divide by mask, old function and then mask which is the registry 2 exists in the code and all. So it stores the function, the value of the GPIO controller. If you see, it does that, and it deletes the aliases after that, and it pops the program controller, program counter, I mean. So we set the GPIO to address registry 0 high, if register 1 is not equal to 0, and low otherwise. So here's register 0 and here's register 1 we created. One is for the 0 one is for pin number, and the pin value is registry 1. Now we compare the pin number 53. So it compares registry 0 with 53 because there's only 54 pins, as I talked about previously. The same thing as right over here, which I used. He used the same code for Alex Chadwick. So yeah, it just uses the same similarity code that it was used previously before. So it uses a pin bank and then create the alias and removes the alias after it's done. So if the pin is off, it will do the same function. So if it's if store bit is at 40 away, then it will turn off the pin light. It will turn off the pin off, but the light will turn on. If the value is 28, then the pin will turn on, but the light will turn off. So we set the program counter back to the value of return address. Now I'm going to go over the main file for lab 5 Raspberry Pi. Starts with the system directives. Then we do the move stack pointer with this address, and then we move the registry with number 16, register 0, register 1 with number 16 is the pin number for the GPIO port. Then they use pin number 1 for registry 1, and the pattern it uses is R4 as the alias, and then loads the pattern equals the pattern, which into the registry 4. You could see that section for data for pattern, and then loads pattern sequence for registry 5, and moves the sequence number to 0, which loads registry 0 into registry 5. Keep track of the sequence position. And then we loop the code again. We repeat the same process again with registry 0, which pin 16. Then we move to registry 1 with pin 1. Do the sequence again. Shift registry 1 left by sequence number, and registry 1 pattern puts it at non-zero, basically. If there is one if and only if there is one, and then we use the loader again. If registry is at 1 million, the sequence time is 250,000 microseconds. So we wait, and then we loop the process forever, implementing the counter, sequence counter, and then once it reaches 32, its bit pattern becomes 100,000, ending causing it to return to 0. all patterns less than 32. So basically we get this at sequence 1 and sequence, I believe this is for the binary number, not a binary but like some kind of, I believe, color. So in the data section of kernel image, it will store a pattern to flash the LED. So basically it's going to use this code, binary, which will be placed to output the LED off on I'm going to explain system timer .s file, and it's pretty straightforward. It gets the global get system timer base, and then it loads the registry 0 to this address, and then it gives the control and clear the timer channel if it matches. And then we move the return address to the program counter, and then we get the global will get the timestamp plus the return address, and then get the system timer base call function, and then we load the registry 0, registry 1. Registry 0 uses pin 4 from 0 to 8, from 0 to 7 I mean, pin 4. It must be stored across 2 registers. Then after that we pop the program counter. So now we do global wait for a number of microseconds before returning. And we're gonna do delay with registry 2 and move the delay registry 0, copying it into registry 2. Then we push the return address, get the global timestamp again, which is called gets timestamp, and we start the request registry 0, registry 3 I mean, and then we move registry 0 and give registry 3 value of registry 0, and then it loops again, repeating the process. So it's gonna elapse registry 1 and sub-elapse registry 0 to start subtracting registry 3 from registry 0, and then it compares the elapsed delay. Compare if delay elapsed. If not equal, then continue, and then we loop if elapsed, and then delay continues again. So then we just pop the program counter and also delete those aliases for delay and start. So I'm gonna go into my tool, which I'm already inside the bin file directory. So I'm gonna do make clear clean. Okay, I think I already deleted everything. Let me double check. So let's go to my files. Yeah, I deleted everything. So I'm gonna go into my make, copy the source, into my bin file. I make first based on my maybe comments and I commented it the right way. So I'm gonna go and use my original file, I guess, because I don't have time to look. Okay, so I'm gonna delete that, delete this. So I'm gonna go to the fifth. Yeah, let me go over here, get the fifth version if I have it still. Okay, so I'm gonna have to download it, looks like. So I'm gonna pause the pause record. So I got these files. I'm gonna copy them into my bin file. Paste. I'm gonna go and run my make and get this, which I need to append the line for the arm. Highlight that up to gpio.s, copy, which I already did, paste, and press enter. Now do make again. I'm getting the error. I'll replace the file. Make file recently supplied. So I'm gonna go into copy and paste. So now I'm gonna go again to make, and it looks like it built successfully. So now I'm gonna bring my flash drive, card reader. Okay, 1 minute. Plug it in again. Okay. Now I'm gonna send it to G drive, and the file is bigger than the previous file. If you look, 300 bytes, that one's 284, so I replace it.